Hi guys, welcome back to the AP and YBTC tutoring series, and today's episode will be about periodic trends. This is actually the first video I'm going to make in this electronic style, and I'm thinking maybe I should turn the channel into this kind of videos. So tell me your opinion on this. Anyways, let's get going. So if you guys remember from last video, we talked about the periodic table and how it's arranged in distinct groups or columns and periods or rows. Now, a side effect of this is that you actually wind up seeing a bunch of predictable trends. And the point of this video is actually to discuss many of those trends and how it changes based on the atomic structure. So the first trend we're going to be examining is called atomic radius. The atomic radius is a simple concept. It's basically just how big your atom is. Now, let me pull up the periodic table. This is borrowed from ptable.com so that you guys can see color and have a better visual view of what it looks like. So I know it can be a little complicated. This is 6 rows of the periodic table filled out. So even for the AP, since you only have to know the general idea on how it works, don't pay attention to much of the detail. You guys can look at the general colors. So pause, take a look, see where the colors are lighter or darker, and then you can feel free to come back to the video. So now that you guys are back, I'm sure you guys have noticed two things. The color becomes darker, i.e. the atom becomes bigger as you go towards this bottom left corner. And you also may have noticed that the color becomes lighter, i.e. the atom becomes smaller as you go towards the upper right corner. Now let's zoom in and examine this in a little more detail. So I've zoomed in on rows 2 to 4 of columns 3 to 18. You can see everything from boron to neon on the top row. And I'm sure you guys can notice the radius of these atoms actually shrinks as you go from left to right. This is no coincidence because as you go from left to right, you have the same number of shells, but you have more protons in your nucleus. So since you have more protons, you have a much stronger charge that's pulling on your electrons. So basically, it's kind of pulling the outer electrons in closer to the nucleus. So that's why as you go from boron to carbon, nitrogen, all the way to neon, your atom is going to get smaller and smaller and smaller. Now, as for the second trend, you may have noticed that as you go down, so for example, from neon to argon to krypton, the atom becomes larger. Now, this is explained just from the number of electron shells. Obviously, argon is in row 3, neon's in row 2. So argon has 3 electron shells, neon has only 2. And the fact that argon has this electron shell on top of it is actually big enough to counteract those extra protons it gets. So that's why as you go down the group, you get an extra shell. So obviously, you become a much bigger atom. Now that we got a good view on atomic radius, we now need to think about ionic radius. So this idea is pretty simple. The idea is that if you have an ion, how does that compare to other ions or other elements? So let's start pretty simple. So let's do fluoride and neon. So as we already know, fluorine is larger than neon. But now we're going to shove an electron onto the fluorine. So we have fluoride instead. And you guys may have noticed, if you count the electrons, you'll notice that fluoride and neon have the same electron configuration. So fluoride has 10 electrons, neon has 10 electrons. So we call them isoelectronic species. Iso means the same, electronic because, electronic structure. So now they're going to ask you, which is bigger, fluoride or neon? Pause the video and think about it for a second. So if you're back, the answer is actually that fluoride is much larger than neon. I mean, it actually makes sense because as we already saw with the rows, as you go from boron to neon, you get more protons, so the atom shrinks. So now fluoride has 9 protons, neon has 10. So obviously the 9 protons are going to have less attraction to those electrons, making fluoride a bigger species than neon. Now, something interesting arises when you're asked to compare fluoride, F minus, and fluorine, which is just F. Now, try to find out which is the larger one here. All right, so now you guys are back. This one's actually a little bit more tricky, but once you understand it, it becomes super easy. So if you add an electron to fluorine, you get fluoride, obviously. But as a side effect of adding that extra electron, notice how there's a bit more repulsion among the electrons in the ion. And because of that, the fluoride ion actually expands a little as it gains that electron because the repulsion is pushing all the electrons away from each other, thereby expanding the atom. So fluoride, the negative ion or any other negative ion version, is bigger than the uncharged version of the atom. Now we have to look at the positive ion. So let's bring lithium and lithium ion into the board. And now we want to compare which is bigger, lithium or the lithium ion. So this one's actually an easy one. So if you notice, lithium has 2 electron shells. Its only electron, or its only valence electron is in the outer shell. So when lithium loses that electron to form the ion, you basically just got rid of your entire electron shell. So obviously, you're going to be way smaller than a normal lithium atom. Now, this is also true if you partially ionize an atom. So even if you have something like boron and you turn it into B+, it will shrink a little bit because, again, less electrons means less repulsion. They can squeeze in a little bit tighter. Now, as a final comparison, let's compare lithium ions and helium. So helium with no charge. Now, if you remember from fluoride and neon, you'll notice that helium only has 2 protons, but the lithium ion has 3. So lithium ion is actually smaller than helium because the more protons equals smaller size. All right, so the next trend we're going to be looking at is called electronegativity. So before we get into the actual trend, we got to define what electronegativity is first. So electronegativity is a simple idea. So I have water right here, and we know that each of these atoms is surrounded by an electron cloud. And the overlap of these electron clouds are what creates the bond. And the idea of electronegativity is that the higher electronegativity you have, in this case, oxygen has the higher electronegativity than hydrogen, it'll actually pull the electrons from the bond more towards itself. So the electrons are actually spending more time around oxygen, the more electronegative atom, than around the hydrogen. A side effect is that you get a partial negative or delta minus on the oxygen and a partial positive on the hydrogen, which is why water is a polar molecule. Now, going back to the periodic table, this is again borrowed from ptable.com. And as you can see kind of a similar trend. You can see as you go down to francium on the bottom left, the atom becomes less electronegative. As you go all the way up to fluorine on the upper right-hand corner, it becomes more electronegative. So let's break down this trend again with the same portion. This time I cut out neon, argon, and krypton just because they don't have data on this periodic table. But as you can see, pretty easily, there is a trend as you go towards the right, now you become more electronegative. And it's actually an easy explanation. Again, fluorine has more protons than oxygen, nitrogen, and carbon. More protons equals stronger pull on the electrons. Obviously, stronger pull on the electrons, they're going to pull electrons away from chemical bonds as well. You can also see this vertically. So as you go down from fluorine to chlorine to bromine, the electronegativity is now decreasing. This is also true again because chlorine and bromine have more electron shells, and these extra electron shells make the outer electrons farther from the nucleus. So it's going to weaken the pull of the nucleus on those electrons in the bond by quite a bit. Our third trend is called ionization energy. So before we get into the actual periodic table, again, we're going to quickly describe it. So the ionization energy is the minimum amount of energy that you need to knock out the most loosely held electron in any atom. Of course, the atom has to be in the gas phase for consistency and standardization. But the idea is that this is the minimum amount of energy you need to knock an electron off of some gaseous atom. So now let's pull up the periodic table again. You can see the trend here is a little bit more complicated. So we're going to have to analyze this a bit more carefully. But you can actually see here, you can still see that cesium and francium have the least amount of energy required to knock out the electron. And of course, helium, fluorine, neon, these guys obviously are hardest to knock electrons off. Now, for better examination, I actually decided to include the other side of the periodic table, so lithium, sodium, potassium, in our analysis as well. So let's bring them all up. And as you can see, you see a general trend. It's you generally see that as you go to the right, you become harder to knock the electrons out. Obviously, again, more protons in the nucleus, the electrons are bound more tightly. Obviously, you need more energy to knock them out. But we do see two major exceptions. So beryllium right here has a higher ionization energy than boron, and nitrogen has a higher ionization energy than oxygen. So now we have to analyze those. And to make that easier, I put the electron configurations on top of each column. So if you look at boron right here, you can see that boron doesn't have s electrons anymore. It has a p electron on top of its two s electrons. And that means that because the p orbital is higher in energy than the s orbital, the boron atom actually has a slightly weaker pull on the p orbital, making it easier to knock out. This is also true with aluminum and gallium, as you can see, compared to calcium and magnesium. And then we have these elements. So nitrogen, phosphorus, and arsenic also have a higher ionization energy than oxygen, sulfur, or selenium. And that one has to do with Hund's rule. So if you remember Hund's rule from one of our previous videos, you remember that a half-filled configuration is more stable because all of the electrons are unpaired. They don't want to get paired because of repulsion. So when nitrogen is ionized, you're breaking that half-filled structure. So it's not exactly going to like that. But when you ionize these three, so oxygen, sulfur, and selenium, you actually form that half-filled subshell. So oxygen, sulfur, and selenium, it's a bit easier to knock that electron out just because you're making it a little bit more stable. The column trend is still pretty consistent though. The electrons are easier to knock out for chlorine than it is for fluorine, and bromine than it is for chlorine, because the atoms are larger, the nucleus is holding on a lot weaker. So it's a lot easier to take out those electrons. Now, if you remember from the definition of ionization energy, it's the minimum amount of energy to remove the most loosely bound electron of an atom. That means that as we continually remove electrons, it'll become harder and harder to remove them as we become closer to the nucleus, as we go into the core electrons, once we've exhausted the valence electrons. So you can actually ID elements based on their ionization energy data, or at bare minimum, get what column they're in. So here I have sodium as an example. So if you look at sodium's ionization energies, the first ionization energy is the energy you need to knock out its first electron. The second ionization energy is the energy you need to knock out that second electron, and so on and so forth. You can actually notice here that the gap between the first and second ionization energy of sodium is massive. It's just absolutely massive gap. And that's actually a simple reason for this. It's just because sodium has one valence electron. That's the most loosely bound electron. So once you exhaust that, when you get to your second ionization energy, you suddenly need to invest this massive amount of energy to like rip it out of its neon core. So if you have this data, you can actually find what column it's in. Since the gap is massive between first and second, sodium, we can conclude, has one valence electron, and that is true. Sodium does in fact have one valence electron. So now let's try practice. So I have 5 ionization energies for a certain element that I picked. I won't tell you guys right now. And I want you guys to find which column it's in based on the ionization energy. So we're only going to count 13 through 18 and 1 and 2. So out of those elements, which column would this element be in given the ionization energies? Right, so you're back, I hope. And so if you look at the chart here, we can see there's 2 reasonably sized gaps. So the first to second is a pretty decent sized gap. But we also see this huge one between the third and fourth ionization energy. Now, the gap between the third and fourth is huge. That's the characteristic gap of going from one shell to the next. That is what we're looking for. So because the gap was at the third and fourth, we concluded this is in group 13. In fact, I chose aluminum for this. Aluminum is in fact in group 13. And the reason why the gap between the first and second was large was just because you're going from a p orbital to an s orbital, which the s orbital is lower in energy. You need a bit more energy to yank the electrons out. The last trend we're going to be looking at today is called electron affinity. Electron affinity is simply the energy that's released when an element gains an electron. So when it goes from gaseous X, gains an electron, and becomes gaseous X minus anion. So this trend is arguably the most complicated out of all of them. So let's bring up the periodic table. And as you can see, this is kind of messy. So you can see we kind of get a trend as we go up to fluorine. It is most electron affinity. And then we have all these columns with like zero. So zero can either mean it doesn't release energy at all, or it need energy to push the electron in. And so this is going to need more analysis. So let's take out a segment of the periodic table here. And then let's put the valence shell structure right on top of it. So that then we can see two things. So generally we have a horizontal trend as we go. So as you go horizontally, there is an increase. And then we have beryllium and magnesium. So let's take care of these guys first. Why are they not willing to take up the electrons when lithium or sodium are? And the answer is because if you look at the shell structure, you can see when beryllium and magnesium gain the electron, they have to put that extra electron in a higher energy, p orbital. You need to invest energy to promote that extra electron into the p orbital. And because of that, you just need energy to push the electron in. So it's not going to spontaneously gain those electrons. Another thing we probably noticed is that nitrogen releases surprisingly little energy, even though it's such an electronegative element. What's going on with that? If you look at the shell structure, you have 3 electrons in the p orbital. Again, you have the same Hund's rule situation. We have 3 electrons in the p orbital. That's half full. They're not paired. That's extra stable. So when you put an electron on there, you're disrupting that. You're forcing one of the electrons to pair with the new electron. That causes repulsion. That causes instability. So nitrogen doesn't release as much energy when it gains that first electron. That's also partially why carbon has a higher electron affinity than oxygen, because carbon, if it gains the electron, it becomes, S2p3. It becomes stable with the half-filled orbital. Now, one last thing we have to cover here. So if you look at the periodic table, again, if you lean towards the right side, you notice that for some reason, sulfur and chlorine have higher electron affinities than oxygen or fluorine. What's going on with that? We normally saw oxygen and fluorine to be the smallest, the most electronegative, the hardest to ionize out of these. But now, somehow, sulfur and chlorine are the ones that are most happy with an electron. The answer here is actually really simple. The answer is the second row elements, so boron to fluorine, are very tiny. And this time, the size actually goes against them. This small size means that there's a lot of electron-electron repulsion, meaning instability. So when fluorine gains the electron, it becomes a little bit more unstable because of that repulsion. Chlorine right now is sufficiently large enough where it has a strong tendency to gain the electron, but it's large enough that it can handle the repulsion. After that, though, if you were to extend the periodic table down, you'll see that as you go to bromine, iodine, and astatine, the electron affinity goes down. So there you go. That was periodic trends for YBTC and AP Chemistry. Thanks for watching. See you guys in the next video.